Right, we're ready now. In your book it's section 5, and here we are, calculus. Dealing with a little bit of theory, some of the rules, and a few examples that you'll be required to deal with. Now, calculus basically involves a knowledge of two processes, if you like, procedures, differentiation and integration. And what I thought I would do is, first of all, we can try giving you some ideas about rates of change. So if we have a look at this little graph, I'd prepared this earlier, you see, so this is simply a graph of y equals 3x. Now if we were to sketch this, it would be very simple. We've got the y-axis going up here, the x-axis coming along here, y equals 3x is a function. So it goes through the point 0 because when x is nothing, y is nothing. When x is 1, 1, 3 is 3, it goes up to the point 3. So this line doesn't change, it goes up all the time at the same rate, if you like. So the gradient, which is the letter m, is 3, the slope is 3. Now that's quite simple. If we have a look at something a little more complicated, let's have a look at y equals x squared. Now clearly we see that this is going to be a curve going up to infinity, just keeps going forever. When x is nothing, y is nothing. When x is 1, 1 squared is 1. When x is 2, 2 squared goes up to 4. When x is 3, 3 squared goes up to 9. Now, without knowing anything about differentiation and integration rules, we can in fact draw a line which is called a tangent. If I drop a line, if I'm very careful, I can drop a line which just touches this point here. Ever so gently, it just touches it and it comes down, continues straight down. And I find that if I've drawn this curve as accurately as possible, this tangent as fine as I can, it'll come down at 1.5. If I now draw this line up to 9 from 3, the number of units here is 9 minus 3, okay, sorry, 9 minus 0, which is 9 units. This distance here in the y-axis is the same as this one, which is 9. So 9 divided by this distance, which is 1.5, is actually the gradient. Okay, so 9 by 1.5 gives me the gradient of 6. Okay, this will be quite useful in helping you to understand the rule that we come to here. Now, when we come to differentiate, for y equals 3x, we find that a change in y for a change in x equals 3. For y equals x squared, a change in y for a change in x equals 2x. And so when x equals 3, 2 3s are 6, this gradient here is actually going to be 6. Now, if we have a look back at the notes in the book, it hopefully will begin to make sense. What we've got here, a little bit of introduction, the two procedures. Now, what we're going to do is to look at differentiating by powers. And the basic rule you've got to understand is that you multiply by the power and reduce the power by 1. So let's have a look at an example. If the examiner or the lecturer asks you to differentiate this particular function here, then this is a solution. Y equals 5x cubed plus 6x squared minus a half x plus 3. The solution is as follows. We write down dy dx. Now sometimes that may be written, depending on who your lecturer is. Sometimes some lecturers do it like this, dy dx, and some books use that. Others even use this, delta y, delta x, but mostly we're just writing now dy dx. Okay, this is the term that you'll come across most often than not. So that's what we're using in the book, dy dx. So let's see how this rule applies. Multiply by the power, reduce the power by 1. So 5x cubed becomes 3 times 5, and the power is dropped by 1. So 3 5s are 15. and 3 minus 1 is 2, so this becomes 15x squared. Let's have a look at this one. 6x squared multiplied by that power, 2 6s are 12, 2 minus 1 is 1, x to the 1 is just x, 6x squared then is written as 12x. Minus a half x, there's a power there of 1 which we don't write in, we assume we all know it, so it's assumed that it's there. 1 times minus a half is minus a half. 1 minus 1 is nothing, anything to the power nothing of course is 1. So minus a half x becomes minus a half. Now the interesting thing here is that 3 is looked on as a constant. So that differentiates to nothing because there's no x term. However, for those of you that are a little bit more inquisitive, let's have a look at this. 3 equals 3 times 1. But the 1 can be represented by x to the 0. Anything to the power 0 is 1. So the 3 can be written as 3 times x to the 0. So if we multiply this by 0, we've got this. Nothing times 3 multiplied by x to the 0 minus 1. So effectively we've got nothing times 3 times x to the negative 1. But anything multiplied by 0 equals 0. So that's why the constant drops out. So here we go. There's a little note to remind you. Note here that constants like the 3 above differentiate out to 0. The reason being is because there is no x term. So if you remember that, that's a quick way of working the problem out. Let's do this one at the bottom here. Find the derivative of a function in x, which is 3x squared plus 4x plus 100. Now let's have a little note about this one. Sometimes you might get this y equals x cubed, etc., etc. So when we differentiate, we would write down dy dx. However, in this case, we have f, which stands for a function in x, equals something. So where there's no letter, where no y exists, we simply can write down f dash. F dash is the first derivative. If we have to go again, then you may see f double dash. Okay, and we'll come across that a little bit later on as well. Here we see the f dash. Okay, so we want the first derivative. We want to find the derivative of this particular term, so we differentiate this. So 3x squared becomes 6x to the 1. 2 3s are 6, 2 minus 1 is 1. 4x, 4 times 1 is 4, 1 minus 1 is nothing, so 4 times 1 is 4, and the 100 is a constant. So this one now you can do very simply, it just drops out. If I turn over, let's have a look at the next. This one now, again we're looking at the derivative here. So I'll just write this out a little bit more clearly for you. Okay, now the examiner asks you, find the derivative of f function of x. Now this is read as the cube root of x minus 2x squared plus 4 over x. Okay, now the first thing we have to do is to rewrite this in a usable term. So I'll write it out here and we'll see what happens. Okay, so function in x. Now another way of writing the cube root is x to the 1/3. 2x squared is self-explanatory. Now this is another tricky little one. 4 over x can be written as 4 to the x minus 1. Okay, now you must be conversant with these particular terms. Just remember that this is the same as the cube root of x, and this is the same as 4 over x. This is just a clever way of writing a fraction. And now we can proceed. Okay, we're in complete control now. We can actually do this. So f dash x, this means the first derived form, is going to be as follows. Multiplied by the power, reduce the power by 1. Multiplied by the power, reduce the power by 1. Multiplied by the power, and reduce the power by 1. You've got to be very careful here. See, you've got to watch what your signs are and check this out all the time. Here we go. So now we get this together. This is going to be 1/3 of x to the minus 2/3. You've got to be good with your fractions. Minus 2 2s are 4, x to the 1, we don't bother putting the 1 in, and this will be minus 4 x to the negative 2. Minus 1 is minus 2. And this in fact is the answer that's given in your book. This will also be the same as this. You could write this as 1 over 3 x to the 2/3. If it comes below the line, then it's a positive. Minus 4x minus 4 over x to the 2. This is just an alternative way of writing the answer in your book there. And be prepared to use that one as well. Now, we said a few minutes ago that sometimes what you've got to do is in fact differentiate twice. Okay, this comes up usefully in some of the situations where we have to use speed and velocity, distance, acceleration. Okay, so let's have a look at the one listed in your book there, the second order derivative. Alright, now I'll just show you this one. Here we are. Find the second derivative of this function. Right, the solution, here we go, and notice what we do. We put out dy dx, and we can do this very quickly. This is going to be 3x squared minus 2 2s are 4x plus 5. The 7 drops out as a constant. So this is the first derivative. This is the first derived form that we have, but now we have to do it again. To show that it's a second one, we write this out as d2y. This is the second derivative of y with respect to x, dx squared. So 2 3s are 6, minus 4, 6x minus 4. Now these ones are very simple. Any constant drops out, and these just keep simplifying according to the rule that we've just learned. Now on the next page we've got the particular case that I was mentioning earlier. Okay, if we consider distance, which is a symbol s, velocity v, and acceleration a of a moving body, then the average velocity is the change in distance over time. So the average velocity here is seen as a small change of distance with respect to time. So at any given time, the instantaneous velocity, the moment it's changing, okay, can be written by v equals ds dt. And by the same reasoning, if I go one step further, by the same reasoning, acceleration will be a change in velocity with respect to time. So let's have a look at this example, which is laid out nicely. A body moves s meters in t seconds and is described by this function, s equals t cubed minus 7t squared plus 3. We have to find expressions for velocity and acceleration at any instant, and then we've got to find v and a after 5 seconds. So here we go. Solution. Write out what you're given, s equals t cubed minus 7t squared plus 3. Now this is an easy one. We can pretty well do this in our heads. Okay, so this is going to be ds dt. So this says a change in distance with respect to time. Well, distance over time is velocity. So this has some meaning now. So we can put this in ds dt equals v. And the velocity now is found by differentiating this term. 3t squared minus 14t, and the 3 drops out. So therefore, or in other words, velocity is 3t squared minus 14t meters per second. Okay, stick with the units. Now, if we find the change of velocity with time, we're finding its acceleration. So dv dt now equals a. Differentiating this quite simply becomes 6t minus 14. So acceleration is 6t minus 14, but this is meters per second squared. Now the last part of the question says find v after 5 seconds and find a after 5 seconds. So we simply put the 5 into these terms that we've got, work them out carefully, and we get 5 meters per second for v and 16 meters per second squared. Okay, so that one is a good one to study for a second differentiation. The next one at the bottom there is very similar. Displacement s in time t is given by this function. Find the velocity after 2 seconds, and also the time taken for the body to come to rest. So when it's come to rest, that means there's no speed. Let's have a look here, and the solution is laid out quite nicely for you. We'll just drop it back. Here we go. Start with what you're given. S equals 40 t minus 5t squared. So the change of distance with time is 40 minus 2 5s of 10t. Okay, this is now velocity. So when t is 2, 40 minus 20 is 20 meters per second. Now, when v is nothing, we put nothing equal to this, and this involves a little changeover. The minus 10t can come across and become plus 10t. 10t equals 40, so t equals 4 seconds. How you would show that is as follows. I'll just put this down. 0 equals 40 minus 10t. Remembering what we've gone through before, alright, minus on that side becomes plus, so quite simply. And then I can divide this out by 10. T equals 4 seconds, which is what the answer is in the book. Now, very quickly, we can have a look at differentiating other terms. In the book, these are ones you'll have to learn. Differentiation of what are called the trigonometric functions, okay, sine, cos and tan. These are well known, and most textbooks will have them written down. These are ones you should learn, and I've given some examples here. So wherever you find this particular term, check out what the derived form is in here. If you have to do it twice, again, put the term d squared y, d2y and dx squared and work it through from this particular table. If we have a look at some of the others, these are examples involving the same sort of thing: sine, cos, tangents where necessary, and all of these steps have been sorted out for you, working through the first differentiated form and then doing it a second time in case your lecturer or examiner requires that of you. Also, you may come across some problems that your lecturer wants you to deal with involving exponential and logarithmic functions. These are sometimes encountered in certain types of problems. Again, get used to them. Y equals natural log x. This is a form that you simply learn. All right, dy dx is 1 over x, and e to the x, interestingly, differentiates to itself. Again, some of these examples are listed out here for you to follow through, and all the solutions are given in your booklet. We then come to something here on the next page called the product rule. Now, in most of the schools and colleges of the states and territories in Australia, the better quality courses will give you instruction in how to use the product rule, the chain rule, and later on the quotient as well. So it is an expectation of AMC that you students will in fact have had some exposure to these rules. Whether or not the lecturer decides to use them or not is at his or her discretion, but it's a good idea to familiarize yourself with these rules simply because the vast majority of grade 12 courses cover them. If you do happen to come across some more difficult problems, then these 3 rules that we will deal with in a few minutes often help you to get out of a difficult situation. Now, I'll go through the product rule first. We'll have a look at this and see what's involved. So here we go. The product rule is very useful in differentiation if you've got some more difficult types of problems. First of all, I'll show you an example here. Let's say y equals x minus 3, bracket, x plus 2. Now, basically, if you're asked to differentiate this, you can do it in 2 ways. You might want to use the product rule, or you might want to use method 1, which I'm going to call expansion. If you're good at expanding 2 brackets, then the expansion method is quite good. So let's have a look at this. Y equals x minus 3, bracket, x plus 2. This expands out. Remember what we did before in the previous lesson. Step 1, step 2, step 3, step 4. This comes to x squared. This is plus 2x minus 3x minus 6. Bringing these together, we get x squared minus x minus 6. I'll just check my notes, that's looking good. So the brackets can be expanded to give you this. So therefore we're asked now by the examiner to do this. Can we differentiate y equals x squared minus x minus 6? And you say, yes, I can. You simply say, right, dy dx will equal 2x minus 1. Remember, multiply by the power, drop the power by 1. Multiply by the power, drop it by 1, and this simply cancels out. So that's fine. Now, why do we need the product rule? Well, the product rule in your book, and we'll bring this in here, has this little complicated explanation here, but it's quite simple. What we do is we let one bracket be u, one letter, and the other bracket be v. So v multiplied by the du dx, the differentiated form of the other bracket, plus u multiplied by the differentiated form of the first bracket will give us our answer. Let's see how this works out in practice. So I'm going to say, this is method 2 now, the product rule, y equals x minus 3, x plus 2. Okay. Now we designate one of these can be u, and this one can be v. So the differentiated form, which will give us our final answer, dy dx, I'll go straight to that. Okay. If we do it in the order in the book, it'll be v, which is that, du dx. Now du dx is the differentiated form of this, which is simply 1 because there's only one x there. Multiply by the power, drop it by 1, plus u dv dx. And again, this differentiates to 1. This is quite a nice straightforward one. So this will give us x plus 2 times 1, which is just x plus 2. X minus 3 times 1 is just x minus 3. So here we have 2x minus 1. So therefore the differentiated form of this, as seen by the product rule, is this. And notice, fortunately, we've got the same answer. Now I've shown that because sometimes it's easy. Okay, sometimes you might have two terms like this. You can get away with it by multiplying it straight out, the expansion. Okay, there it is. Expand it out, and it'll give you the correct answer. This is to show you, this method here is to show you in a simple way that the same method can be used in any particular problem if you've got brackets like this one. Okay, this just shows you that the answers are in fact completely and utterly identical. Now in the book you'll see that we've got something that's a little bit more complicated. So to find the derivative of 3x squared minus 1, that's the first bracket, 2x cubed plus 3, that's the second bracket. If you're good at expanding brackets, you can in fact take the time, and this would be a good exercise for you to do in your own time. I'll leave that as an exercise for you to try in your own time, to expand this out, differentiate it, and see if you get the same answer as this one. Of course you should, but this is a lot easier to use because the product rule is designed to simplify the working. Okay, and there are some problems that become a lot more complicated than this, and so the product rule is quite, in fact, quite useful. Okay, what happens if we take the product rule and we just change it up a little bit to give us the next one, which is extremely useful, and I'll show you why. This is called the chain rule. Now the chain rule is very similar to the product rule. Let's have a nice simple one. So let me give you this, y equals 3x minus 1 all squared. Okay, I've chosen this one because it's nice and easy to show you by expansion. So method 1, if we expand this out, quite simply this means 3x minus 1 bracket 3x minus 1, which if we then expand this out as we did before, we get 9x squared, okay, minus 3x minus another 3x plus 1. So putting these together we get 9x squared minus 6x plus 1. The examiner then says, okay, will you please differentiate this? 6x plus 1. So you say yes, we can do this. 2 9s are 18x minus 6. And that's fine. Now with the chain rule, what we now do is we say this. This is our method 2. Chain rule, we say let 3x minus 1 equal u. Or it could be any other letter, but u is useful. So now we can say, therefore, y equals u squared. Okay? So when we want dy dx, what we're looking for now is we want to find du dx. We differentiate this, and then we multiply by this one, which is going to be dy du. So let's do this one first. Du dx, this one here, is simply going to be 3, and dy dx is going to be multiplied by this one, which is 2u. If I now substitute that back into here, I get 3 multiplied by 2, bracket 3x minus 1. So what I'm saying now is this one. This is going to give us, let's have a look, 2 3s are 6, bracket 3x minus 1, close the bracket. So finally, dy dx is going to be 3 6s are 18x minus 6. And of course this one was chosen because we now see that they're completely and utterly identical. Okay. Now I'm going to show you another one in the chain rule here. Let me bring this down a little bit for you, where it's a little bit more complicated. The examiner now says here, can we differentiate this? Y equals, let's have a look at this one, 3x squared minus 4 all to the power 4. That's good. Okay, now you could in fact write this out 4 times and multiply it out, but that's far too tedious and there's a big chance you'll get it wrong. Too easy to make errors. So this is what we do. Let 3x squared minus 4 equal u. Therefore y equals u to the 4th. So now we go through what we did before. Dy dx equals dy du. So we differentiate this one and then multiply it by du dx. Because you see the du here will in fact cancel out. So let's do that. Now dy dx, sorry, dy du is going to be this one. So this will be 4u cubed. Do you see why? 4 times, bring the 4 down, multiply by the power, which is 4, and reduce it by 1. And du dx is going to be this one, which will be 6x. And the 4 disappears. So just check through that again to see that you agree. Now we can substitute this term back in for u. So what we've actually got is this. Multiplied by 6x. And we can bring this forward. This will give us 24x. 3x squared minus 4 all cubed. Now, the lecturer or the examiner might say, find this value, this is typical, you have to use it for something, when x equals 2. So what you now do is you say, right, we'll put 2 in place, this equals 24, multiplied by 2, 3, multiplied by 2 squared minus 4, all cubed. And if you carefully work that out and put that into your calculator, that will give you, in fact, 2, 4, 5, 7, 6. And I'll leave you to work that out as a calculator exercise. It's going to be 48. Okay, this is 8 cubed. So if you wanted that, this is 48 multiplied by 8 cubed. And finally, your calculator will, in fact, confirm the answer. Okay, let's have a look then in the book. This is the chain rule. This is a form of the product rule which is often useful to use. Okay, and this one, you see, I've even used a more complicated example in the book, but it's the same as the one that I've just shown you. This is more complicated because we've got the power 6. Now, when we work it through, quite simply, here we are. We start with the term that's given. Okay, set out what we're going to substitute, work it through, and then, for example, when x equals 1, we can put the 1 in place of here and find the final rule as well. Good. Now the last little rule that you would have come across, most of you, in grade 12 is the quotient rule. We'll go through this one. Or the dividing rule, if you like. I often remember it like that. Now in the book, the quotient rule, again, you have two terms, one divided by the other. Okay, you let one be u and one be v. Normally this one is u is the top one and v is the bottom one, and we're using a form of substitution. Okay, so I'll show you one, a simple one that I've worked through, and we can actually have a look at this one, and then you're ready to do the one in the book. So the examiner says, right, let y equal 2 plus x over 1 plus 2x. The first thing you do is you assign the letters. So this one here, u, and this one is v. Now, to differentiate, this is going to be v multiplied by du dx, which is this, and the differentiation of this form is just 1, minus u, which is 2 plus x, multiplied by the differentiation of this, which is in fact 2. 2x just goes to 2. Divided by v squared, which is 1 plus 2x all squared. Don't bother multiplying this out, leave it as it is. Simplifying the numerator here, the top part, we can write this down. Now 1 plus 2x times 1 is just 1 plus 2x. Minus this is going to be minus 2 2's are 4, minus x times 2 is minus 2x, all over 1 plus 2x squared. This top will simplify, and 1 minus 4 is negative 3, plus 2x minus 2x is nothing. So this simplifies to a rather convenient term of minus 3 over 1 plus 2x all squared. And leave the answer like that, unless the examiner wants you to expand it out. Normally they don't. Normally they're quite happy to leave that. Now let's use this. The examiner then says, okay, can you find dy dx when x equals 1/2? And you say, yes, we can do that. So the solution now becomes dy dx will now equal negative 3 over 1 plus 2 to the half squared, which is going to be 1, 2, 2 2's are 4, which will give you minus 3/4 there. Okay, in case he wanted you to put the number in. Okay, so when x equals 1/2, the differentiated form will give you negative 3/4, and that's the quotient rule. Now, just to show you the one in the book, before we move on to the next section, we'll just finish off here. Quotient rule here is listed out, so we'll go through this. Find the differentiation of this when y equals 3 plus 4x, 1 minus 2x. So here I've informed the examiner, let 3 plus 4x equal u, the top part, and 1 minus 2x equals v. So here we go, the solution. v du dx minus u dv dx, all divided by v squared. When you confirm that this is in fact the right term here, you can in fact put these together. So this is going to be 10 minus 8x plus 8x is nothing over this form here, 1 minus 2x all squared. And I would leave it like